Hello there. In this video we're going to look at the equation of motion for the spring model of a diatomic molecule, determine the frequency of oscillation, and then we're going to discuss a little bit about infrared spectroscopy at the end. Alright, at the time that I'm uploading this video, this channel just reached a very important milestone. We just surpassed 500 subscribers, and this is a really big deal, guys. When I decided to start consistently uploading videos on this channel week by week, that was around a year ago when I decided that. It was very important to me to not advertise heavily the videos being put on this channel. I really wanted to just kind of throw these videos out there and see, if people ended up finding them helpful, they would get on board, right? And I wanted that to happen organically. So the fact that I can kind of see that people are engaging with the channel, subscribing to it, liking the videos, etc., etc., I really am happy to see that these videos are truly helping people, People are getting help, finding them interesting, and subscribing to the channel because they want to, and that's extremely important for me. So thank you, everyone. But anyways, let's go ahead and proceed here. Let's have extra fun with this video, okay? So here we have a spring diatomic molecule. What I've done is I've represented the bond between two atoms with a spring of spring constant K, right? And I'm going to use the example of HCl, right? Where, this little mass here, this could be our hydrogen atom, this mass over here, this could be our chlorine atom, right? And they have a bond between them. And that bond has a spring constant K, representing the strength of the bond. Alright, so to start this problem, what I'm going to do is I'm going to define the origin of my coordinate system. There are a lot of choices that we could make. This is clearly a 1D problem. So what I'm going to do is I'm just going to define a location that I'm going to call x equals 0. Alright, and with this dashed line, okay, this is going to be the x equals 0 location. And so, in theory, we could go ahead and track the positions of each of these masses separately. Okay, so I'm going to go ahead and start by calling this location x1. This is pointing to the first mass. And then I'm going to go ahead and I'm going to go all the way out to m2. Okay, and I'm going to go ahead and call this guy x2. Now, there's a very important concept about this molecule. Notice how there's no net external forces on this system here. So what does that mean about the center of mass of M1 and M2, right? I'm going to go ahead and kind of indicate the center of mass of this system with like this blue X here, right? The point is that this guy here, this center of mass point, it can only translate around with a constant velocity. That location cannot accelerate, right? Because there's no net external forces on this system of particles. So what I want to take a moment to emphasize here is that this origin of my coordinate system is locked with the center of mass of this molecule, right? So if this molecule, it could translate around, but this origin here is going to follow that. And it's just going to move with a constant velocity. And that's going to allow me to just treat this molecule like it's stationary. Okay, this is called entering the center of mass frame of a system. Now, the way that we're going to track the forces on these molecules, because this gets dynamic pretty quickly, right? Because if we have to change both the locations of x1 and x2 simultaneously to keep this center of mass location fixed, there's a really nice way to kind of break this down, okay? So what we do is we imagine displacing one atom at a time. So first, suppose that I had a positive displacement in M1. I'm going to call this delta x1, and then that would shift M1 over to the right like this. If I do this, what's going to happen to M1? Well, look, you just compressed the spring. So what I'm going to get a force pointing this way on M1, right? And so a positive displacement in M1 leads to a negative force. So I'm just going to keep track of the signs here, by putting a minus sign here. I have minus k delta x1. And what's going to happen to M2? Well, if you compress the spring, look, now M2 is going to get pushed out. So all of a sudden I have a positive k delta x1 pushing M2 out. Next, let's go ahead and suppose that keeping M1 fixed, I displace M2. Okay, now have that visual in your mind. M1 is locked in place, it's stuck here, and I'm displacing M2 out some delta x2, right? And now I've got this big M2, it's displaced over to the right here. Now look at this spring, it's been stretched out. So what's going to happen to M2? Oh look, it's going to get pulled in, what amount by Hooke's law? K delta x2. A positive displacement gives a minus directional force, it's pointing to the left. Put a minus sign on there, let's keep track of that. And then on M1, what's going to happen? Oh, I stretched out the spring. Now I'm getting pulled in, and so I'm going to have a force on me, K delta x2. Nice. Go ahead and sum up, superimpose the contributions of these displacements on the masses, and that's going to tell you, the net force for an arbitrary displacement, delta x1 and delta x2 on the masses. Okay, so what's the force on mass 1? F on M1 is going to be equal to minus K delta x1 plus K delta x2, and F on M2 is going to be equal to minus K delta x2 plus K delta x1. You see how I'm just adding these forces together for each particle? Excellent. Right, and this guy here, this is going to equal M1 x1 double dot, the acceleration of my first particle, and this guy here is going to be equal to m2 x2 double dot, the acceleration of my second atom. Now, what I'm going to do is I'm going to write each of these guys out a little bit more suggestively, okay? I'm going to go ahead and write out x1 double dot is equal to k over m1 times delta x2 minus delta x1, and I'm going to write x2 double dot as equal to k over m2 times delta x1 minus delta x2. Right, you see that? Nothing fancy there. I just divided the masses over and I rearranged my terms a little bit. Now, I want us to think about what is delta x2 minus delta x1, right? In other words, I'm taking the difference of my displacement of the second mass minus the displacement of the first mass. Right, isn't that just going to tell me the total stretch of my spring? Okay, so I'm going to call, I'm going to define this stretch parameter. I'm going to call it S. S is defined as delta x2 minus delta x1, right? Run the logic through your head for a second. If delta x2 equals delta x1, right, we get no stretch, of course, right? Because we haven't had a net displacement of either particle. If delta x2 is larger than delta x1, we're going to get a stretch of the spring in the positive direction, right? Right, so I can rewrite both of these guys here. I can rewrite both of these terms. This is S, and this guy here, this is going to be minus S, all right? But now we have this issue here. I still have x1 double dot and x2 double dot. I wonder, I bet I could write x1 double dot and x2 double dot in terms of the stretch parameter S. Let's go ahead and see if we can do just that. All right, and now what I'm going to do is I'm going to indicate the equilibrium length of my spring. I'm going to go ahead and do this in orange, right? So if neither mass is displaced at all, this spring's not going to be stretched out at all. So, and I'm going to pretend, right? I'm going to act as if the spring stretches from the center of masses of M1 and M2, because that's effectively what we're tracking here, okay? And so I'm going to go ahead and call this X naught. This is the equilibrium length of my spring, right? And so what I need to do is using x2, x1, and x naught, I need to write out the stretch of my spring. How do we do that? Well, think about it. What's the length of the spring going to be for some arbitrary x2 and x1? Oh, that's right. I'm just going to take the difference between x2 and x1, and that's going to tell me the distance between the two atoms, aka the length of the spring between them, right? And then if I have that length, I'm going to subtract from that, I'm going to subtract the equilibrium length of the spring, and that's going to tell me the stretch of the spring. Okay, so are we seeing this super duper clearly? I'm going to go ahead and write down our stretch parameter, now in terms, this is now equal to x2 minus x1 minus x naught. What happens if we differentiate this twice? I'm going to have s double dot is going to be equal to x2 double dot minus x1 double dot. X naught is just a constant, so that's going to drop out. So let me go ahead and re-summarize where we're at. I'm going to rewrite these differential equations. I have x2 double dot equals minus k over m2 s, and I have x1 double dot equals k over m1 s, right? And now, right, we can apply this relation here. I'm going to subtract through these differential equations, and that's going to give me x2 double dot minus x1 double dot. And what is that? Oh, right, that is s double dot. And this is going to be equal to minus k over m2s minus k over m1s. Is there a way we can go ahead and like combine these terms together really nicely? Definitely, right? If I have k over m2 and I have k over m1, what I can do, watch this, I can multiply both of these guys by m1 m2 over m1 m2, right? m1 m2 over m1 m2, just multiplying them by 1, cancel, cancel, you know, and cancel, cancel. Look how these terms have the same denominator now, right? This guy's going to be equal to minus k m1 over m1 m2s minus k m2 over m1 m2s. Nice. Now we can pull everything out, right? And so I'm going to have s double dot is equal to minus k times m1 plus m2 over m1 m2 times s. This term here is extremely important. There is a definition called the reduced mass of a system. It's called mu. Mu is defined as m1 m2 over m1 plus m2. I'm going to go ahead and rewrite this differential equation one last time. I have s double dot, let me move this guy to the other side, plus k over mu times s is equal to 0. Beautiful, right? And so we can see here that the stretch of our bond, right, or our spring follows simple harmonic oscillation, right? That's a really important idea, right? Where what's the angular frequency? It's going to be omega naught is equal to root k over mu. Let me box this guy up, right? And so let me go ahead and really emphasize here that the angular frequency here, right, the frequency parameter for my oscillations is going to purely depend on, right, the masses of my atoms, M1, M2, and the strength of their bond, which is captured in this K parameter, this spring constant here, right? And that's key, right? Different diatomic molecules are going to have unique angular frequencies purely based on the relation between the masses of the atoms and the strength of the bond between them, right? And this leads to an analytical technique in chemistry called IR, or infrared spectroscopy, in which we're able to identify molecules with their vibrational, and rotational too. We're not really discussing that very much in this video, but essentially by identifying these modes, you're able to fingerprint, molecules or functional groups that you're looking at, right? So molecules with net dipoles will absorb light based on this omega naught, based on this kind of fingerprinting frequency that these molecules have, right? And specifically, I'm just going to kind of very briefly give us a little insight on some of the quantum mechanics at play here, right? We can show that for a quantum harmonic oscillator, right, as opposed to, a classical harmonic oscillator, we have energy levels, E sub n, defined by h bar omega naught times n plus 1/2, where n is going to be equal to integer values, right? Ranging from 0, 1, 2, ... right? So we get discretized energy levels in quantum mechanics, right? Right, we can excite these modes and transitions between these modes using light, right, where the energy provided by the light is going to be equal to like HF, right? And so that's what you're going to see here. I just went ahead and put on the screen, you know, a IR spectrum of the HCl molecule, right? Even if we consider the quantum harmonic oscillator, this is still a gross simplification of what's going on. We're not, you know, we're not even mentioning, you know, rotational modes or anything of that nature at all. But we can start to get together the basic idea here. And by shooting light at different wave numbers, right, and we can see that these wave numbers are corresponding to light in the infrared spectrum, then these molecules are going to essentially absorb the light at discretized, you know, locations. Like I said, me just bringing up the quantum harmonic oscillator is not nearly enough to describe the full mechanics of what's going on here. You know, it's just to get the basic idea across. We have to consider rotational modes also. I'm going to go ahead and leave a link in the description of the video that talks a little bit more about the HCl infrared spectrum in some more detail. Okay, and you might find that an interesting read, right? But the main idea is that it's really this omega naught parameter here is kind of your key factor that's telling you that there is a unique way to fingerprint different molecules and functional groups based on the masses of your atoms and the strength of the bond between them. If you found this video interesting, found it helpful, let me know in the comments and consider subscribing to the channel. I love to hear about people getting on board. But other than that, thank you so much for watching.